Welcome to Learning Python. So, like we were discussing in the last session, for the same distribution, let's say we take normal distribution or we take uniform distribution. As we keep on adding, more the length of the random variable increases, the size of array increases. We can see it was behaving more like the distribution we were expecting. But it becomes very difficult. We have less number. So how do determine? So there are many tests. So we make many hypotheses, or hypothesis means assumption. So we make many assumption about let's say this distribution follows this data follows normal distribution, or mean is equal to 5 or not, or some other value or not. So these are the kind of hypotheses we can test, and there are some test statistics we use, and we can verify whether it's within a permissible limit or not. Permissible level, typically we keep, we call it p value. You can go much more into theory and see how it's computed, etc. So let's quickly take one example and see how we can test it. So what we will do, we will generate one, we'll generate one random variable with location is equal to 5 for normal distribution, which means mean is equal to 5, scale is equal to 10, and size of 1000. And let's see how the histogram looks like. Okay, we should import our libraries also. So sometime I also forget to import the library, so it's very common thing. So we don't remember you have imported in this function or not. So you can see, because we are generating 1000 random variable, it's looking reasonably like symmetric, like a bell shape curve. Let's start reducing the size and see how it looks like. Now it's not looking, at least visually not looking like. But also when we have less number of variable, like 100, and we have take too many bin size, it will not follow look like a distribution. So there are some optimal bin, etc. we can use. One more thing we can test, not apart from the distribution, what is the mean. So let's compute the mean. What we will do is, I think we have done this exercise earlier also, but we'll try to do it again. So we'll take n is equal to, let's say, 10, we can take 50, 100, 500, 1000, 5000, and we can write for I in n, and we can say size is equal to I. So it means a loop will run. First size will be 10, then 50, then 100, then 500, 1000, and 5000, and we can compute mean of it. We can create one empty matrix. So we can say, let's say, x mean is equal to we can simply write 0. We can import numpy library, and we can store x underscore mean. I hope everything is correct. One, two, three, four, five, six. Why I is going up to, okay, this I is it's part of n, this is not the range. So it will be a good idea to run it like this: range l n, and then we should call it here n I, and then it should run. Yes, it's running. Now we can simply make it float. We expect a value of pi, 5. Mean was we were expecting 5. We can see the first value was very different, very far from the 5. but as we see more and more number of variable, it's stabilizing around 5. But the test can be done at any level. So we'll try test also. We can try t-test also at different level. So we are testing for the 10 sample whether mean is equal to 5. This hypothesis is true or not. For the 50 sample, for the 100,000, for the 5,000 sample. So we see that in all the cases, value of p is more than the threshold. Typically we take 0.05. So it means we can say that mean, yes, for this standard variable mean is closer to the 5, or it's equal to 5. We can assume that safely. So it means our hypothesis is true, and then we can assume this. And we have generated the random variable with assuming 5, so there was no issue, and we got the output that we were expecting. You can try by taking some other number. Let's take, instead of 5, just for the sake of fun, see, take 6 and see what happens. Now also you see there are some cases when it's telling yes, our mean is the hypothesis that mean is equal to 6 is also true. Because what happens when you have a less number of variable, the mean might be maybe instead of 5 it might be 5.5, 5.7 or something, which is not far from the 6. So sometimes it's a statistics and there are some assumptions. The wrong hypothesis also might be true. We are generating random number from a known program. We know how it behaves, and this is supposed to produce the random number following this normal distribution with the mean we have defined. Even then, when the data is less, it's departing from the mean we were expecting, and it's saying mean is 6 also. So there are these cases. That's why we say, at least I feel, in data science is very important. Statistics or all these, these are the tool to do what we want to achieve, but these are not the ultimate reality. So always be careful what p value is, what p value not is. And whenever you are given something, play with it. If somebody is given example whether mean is equal to 5 or not, try with 6 also, try with 7 also, try something else. Try in all the possible ways how you can test to figure out what is the strength and weakness of any given test or any given algorithm. So now let's move to next example. Now we are generating two random variable having the same mean and location, same scale parameter, and we are testing whether these two variable have the same mean or not. See whether in the first example we had t-test for one sample, t-test underscore one sample, which means we are given a sample and we are checking whether mean is equal to 5, 6 some number or not. Here we are checking whether the mean of two variable is same or not. So we have taken 5, 5, and we are getting quite good p value, so we can say it is. Now let's try what will happen if we take 5 and 6. In we expect it should say they are not same, but let's see what happens. It's telling they are not same. Let's try with the small size. It's telling that at 5 and 6 they are same at the threshold of 0.05. So it 0.05 also means there are quite good chances that we can filter out hypothesis true or not, but still there are some chances we can make error. Maybe you want to read about type 1, type 2 and type 3 kind of error, how they impact, etc. So we are only minimize chances of error. We are not making our error 0. So sometimes wrong hypothesis can also be true. We have a mean of 5, we generate another random variable mean of 6, and they will look similar. Okay, so these kind of things we can expect, and you should be careful when we get the field data, because in field what happens, here we can run more and more variable random number we can generate, we can change the size, etc. But in the real life we are given a set of data, we cannot generate it another time. It's not so easy. If go and then collect this almost data in the field, let's say 1,000 sample, took another 1,000 sample, it may take couple of months, lots of resources, so not so easy. It's not just about clicking once again in Python and generating. So we are given some data set and we should do best with it. But when we understand the limitation, this is the best part of synthetic experiment. We can do experiment and generate understanding out of it, which we can apply to limited data we get in real life. So when we know that samples are related, we can use t-test underscore relative. This was when we know they were coming from the independent experiment. We use this experiment, but when we know they are coming from the our related experiment, then we can apply this, and then you can follow the same procedure. So there are three kind of three t-tests you can apply depending upon the situation, and then you get the result. You can interpret the result, but be careful. There are always some chances of error while interpreting. So see you in the next session. But the t-test is quite useful when we go into hypothesis testing and those kind of things. And this p-value you will keep on seeing again and again whenever we do some hypothesis testing. So thank you. See you in the next session.